Hi, everyone. Thanks for joining. This is Jason Key at SB Grid. Today, we've got Woonghee Lee. So correct me if I'm wrong, Woonghee. You are a staff scientist in Madison at the National Magnetic Resonance Facility there. Is that correct?
Yeah, right.
So Woonghee has developed a number of NMR packages. Most notably, I think, the historically important Sparky has gained a new life and a good sort of new caretaker, and he's added on many additional useful tools and developed some standalone software as well. So today he's going to be telling us about Sparky, NMRFAM-Sparky. So go right ahead.
Okay, thank you for accommodating me, Jason, and I also appreciate this wonderful opportunity. I'm gonna share the screen first. I'm Woonghee from the NMRFAM. I'm going to talk about NMRFAM-Sparky, which succeeds UCSF-Sparky that has not been developed for a long time. I officially take this development in 2014. Since then, I developed many features inside of the NMRFAM-Sparky, reflecting the advances in the current animal technologies. So I'm going to talk about this today. So the content will be the NMRFAM-Sparky basics. So it has improved features in terms of algorithms and also the UIs. So I'm going to talk about the UIs that people will get the benefits directly right away. Such as using the mouse wheels or arrow keys that has not been there in the UCSF version, but now they are all in the NMRFAM-Sparky that is much more productive than ever. And then also the automation tools that can utilize for your project, and also the resources that can teach yourself by looking at the videos and then the documentations and so on. So common task in biomolecular NML. So what you will do after getting the NML sample in the tube is going to be the data acquisition on the spectrometers. So you put your sample and then run the pulse program and then acquire the data. The data will be the time domain data that you will process using software packages like the NML pipe in conjunction with the NML draw, or book or topspin, or sometimes you can use VNMLJ and so on. And then you process the data to the frequency domain data, and then you will need to analyze the frequency domain data. That's what you will use for NMRFAM-Sparky for. So you pick the signals and then assign the labels, and then you do titration and interaction studies, and then do the relaxations, measuring the peak heights, and you can do NOE assignment, generating the structural restraints with it, and then calculate the structure. So NMRFAM-Sparky embraces Ponderosa, a CS program that wraps up Explorer NIH and Cyana, so you can do structure calculation fully integrated manner. So you just push some buttons and then you automatically calculate structure. You can easily refine the restraints and then see the NOE peaks and then the generated restraints and all together with the structure. And then once you get the chemical shift assigned, or you have some titration data, you deposit into the BMRB using Edit NML user interface, which will be sooner or later replaced with the new tool. Or if you have associated protein structure with your chemical shift, you use one dip from the worldwide PDB. So it is okay also you provide chemical shift first and then put your structure in the one dip next. So you can do both. So that's going to be the final thing before you publish your paper for data deposition. So NMRFAM-Sparky has its own file organization. It's pretty similar to UCSF-Sparky, but one thing that I like to emphasize is that Sparky home, which is the root directory of your project, can be easily set by two-letter code large R and large D. So by typing two-letter codes, NMRFAM-Sparky can accelerate all of your tasks. So by typing all D, all capital letters, you set up where I'm gonna have all my projects in. So that has to be done by changing the Sparky home parameters in the library file for UCSF Sparky, but that is now explicitly made as a function in the NMRFAM-Sparky. So you set up your Sparky home, then relaunching the program will automatically read that Sparky home to set up your place to work on. And then once you set up the Sparky home and relaunch the program, automatically projects, save, and list directories will be made where you will have your project file that contains your save files associated with that project, and then save files will associated with that UCSF row spectra file. So these row spectra can be included any directory, but I recommend that subdirectory under Sparky home, because when you need to move your data, you can just copy and paste them to other system or directory that will work, because they are all relative path. But if you have file in the other than the subdirectory under Sparky home, then relative path will no longer really reliable. So to make your project reliably portable, then you want to have everything under Sparky home directory. And then the new directories that you can be notified in this file organization chart is that chemical shift reference views. If you type IR in the Sparky, then it will generate the ref directory, and then place these files. These files will show you the chemical shift distributions that you can find in the BMLB. So it gives you synchronized cursors that if you put your cursor on some chemical shift, then you will see how probable that amino acid can be, or certain probabilities based on that chemical shift can be searched in that reference view. So this is the new feature that can be launched by typing IR. And then Pine is the automation system that NMRFAM-Sparky has. So they are all integrated. You just pops up two-letter plugin. EP will pops up the Pine-Sparky 2 plugin that you can run Pine automation system. Now it has the name integrated Pine, which is the Pine 3 basically. And then automatically you can import the results back by just a few clicks of the mouse buttons too. So apparently, like I mentioned a few times about the raw data format processed from the time domain data. So you have frequency domain processed in the top spin in case you collected the data from the Bruker machine and then you process the data in the top spin, then you will have Bruker processed data. Or Variant can make its own processed data. Or if you prefer using NMRPipe, which is great command line Unix pipeline-based tool that you can use many of the good features to enhance your spectral quality, you can use that NMRPipe files as inputs to import data into the Sparky too. So CUI method, the command line user interface method, you just use the handy tools that comes with that Sparky Brook to UCSF or VNML to UCSF or pipe to UCSF. Then you generate that UCSF file can be readily imported to the Sparky project. Or if you need to handle multiple files, there is a new GUI tool called EasyBrook to UCSF or EasyPipe to UCSF that you can select multiple row spectra and then automatic conversion to the UCSF into certain target directory you designate will make your life much more easier. And also there is an NMRFX processor from Bruce Johnson. It supports also generating the UCSF files, so you can use that tool too. And the other feature in the NMRFAM-Sparky is that actually you don't really need to use these methods. You can just open the file, then it will automatically generate that UCSF file in the same directory that you selected to open. So let's say if you open to all file in the SERM directory using this file open FO, then it will open that to all. At the same time, it generates that to all.ucsf file in the same directory. So next time you can open that UCSF file, which is the tile-based data format that makes you more. It is much more efficient file handling method that Sparky utilizes. So you can use that UCSF file generated from that automatic conversion in the NMRFAM-Sparky. So like I mentioned, setting Sparky home is the must-do right now. So it's much more easier than ever. So you just type Alt D and then set up the directory that you want to use as a workspace. And then the next thing is very important thing, but many people does not really even know about this. So you can set up autosave by typing PF, so that is preferences, or if you go to the file menu and then go to the preferences, then you can find this window, then you can set up automatic backup period here. If you type 5, every 5 minutes, it will save your workspace to those save files. So if you have any catastrophic thing happens, the computer died, or the electricity died, or anything happened, you will have the backup there. So that is much more safer way of keeping your data available. Next thing that you want to do is setting up a sequence. In case you're dealing with the protein NMR, I highly recommend using this sequence window, because many of the automatic features now in the NMRFAM-Sparky automatically detects the sequence information you set up using this window. So you don't have to find your sequence file every time when you are running the new automatic features in the NMRFAM-Sparky. So typing SQ and then typing this sequence directly in this window, or you can browse into your directory and then find sequence file and set up sequence file here. So it accepts 3 types, 1-letter code FASTA or 3-letter code with and without indices. So if you have sequence index like the Cyana format, 3-letter code, you can use that .seq as file extension. Or if you don't put any indices, then you just use .txt. So I particularly recommend using first residue number as 1 for the initial analysis, because of many algorithms out there, they support the first residue number as only 1. So you do all the features and then you adapt all the automations until you get all the chemical shift assigned. Using just 1 is fine, and then after that you can easily change by the 2-letter code RLM in the NMRFAM-Sparky. This is the new feature that you can just automatically change all the sequence in your project. So let's say you automatically runs iPine system to get the automatic assignment, and then you really need to change the first residue as 500. You can just use this one RLM to change. Okay, I'm going to use first residue as 500. It automatically readjusts all the sequence numbers. So it will be much easier. So basic access manipulations. Protein NMR, we need to handle, in many cases, 3-dimensional data, or sometimes 2-dimensional data you will need to transpose axes. So there are 2 axes related two-letter codes that you will use. So one is XX and the other is XR. So by typing XX, the dimensions will be transposed. So that means if you have, let's say, 2D HSQC, horizontal axis is H, and vertical axis is usually the nitrogen. Then the way you collected data and process the data, sometimes you will see nitrogen as the horizontal dimension, and then the proton as the vertical dimension. Then in that case, you want to change by two-letter code XX. And then 3D data. So basically, in the 3D data for solution NMR, so main stages are amide, proton, and nitrogen. So you put in direct 15N dimension as the z-axis, and then direct proton as x-axis, and the other guys in direct dimension, C13 carbonyl proton as y-axis. That's basically, you will prefer to use this basic axis order. So you use these XX and XR to make it matching with this basic order usually. So you just change XX to change X and Y dimension, and then XR to rotate whole three dimensions to make it like this basic axis order. That's what you will use these two-letter codes to make it a preferable view. And then you will deal with many experiments. So synchronized view, the two-letter code YT is a preferred way to just set up the synchronization that you move around through the NHSQC automatically. Other experiments correlated with that NHSQC follow that your view changes in the NHSQC, or the other way, if you change the CBCH view, then other experiments like NHSQC or other experiments will follow that view change automatically by setting this synchronization view by typing YT. So you can see that identifiers A here means that, okay, they are all correlated. Okay, and then these are my proton here. This little c means that they are all correlated. So basically, if you open up the experiments, they are none. You don't see any A or B or C. So by clicking these three little buttons here and then click this synchronize, then it will provide this new identifier like A here. That means they are all correlated. By that time, if you move through N15, they will have the exactly same view across the experiments. That goes the same for the other resonances here. So that is very useful. When you select the peak and then type VC, view center, that will make all the experiments aligned. So that is very handy. And then another thing that you want to do is aligning, because of different circumstances, collecting data, or you set up wrong carrier positions during collection and processing, then they deviate, somewhat deviates across, CBCH can be different from this HNCACB slightly, or NNH can be different too. So you want to use alignment option using AL. So that's the next thing that you will use. So the usage of this AL window is selecting two peaks in the two experiments, and then set up the axis that you want to align. So in this window, you see that, okay, I'm going to use a peak in NHSQC. I'm going to change the CBCH based on this NHSQC. So you select the peak in NHSQC, and then at the same time, okay, I'm I'm gonna move this peak matching with this peak. So hold Shift key and select this peak and click this align button here. So that's what you will do. So 3D is the same thing, but you set up 3 axes. So you can see that NHSQC is 2-dimensional experiment. So you only set up 2 dimension here, but this time 3, and then click align button will do the job. And there are one-letter shortcuts. So Sparky is very popular because of that efficient 2-letter shortcuts that you can access all the features by typing 2 letters. And then even more, you can just use 1-letter shortcuts in certain tasks that is useful for just using 1 letters instead of 2 letters. So for example, the function keys are meant to change the pointer mode and the mouse cursors. So mouse cursors will be changed depending on your pointer mode. So let's say if you are in the selection mode, you will see that cursor icon with that box and cross mark here. So that looks like the cross peak selected. So this icon you will see when you are in the selection mode. And if you are in the center pointer mode, you see that dot in the center and so on. So you can really just hide your pointer mode window because you can easily recognize what your pointer mode in by just looking at your cursor. So that is also the useful new features in NMRFAM-Sparky. And so 1-letter keys like contour level adjustment. So if you use these brackets, that contour line gaps will be changed, and this semicolon and then single quotation mark is to change the contour level threshold. So if you click this single quotation, then the threshold for contour will be lower. That means you will have more crowded peaks in your spectral view. And then if you just press this semicolon key, then that increases your contour level threshold, then you will see sparse peaks and much sharper peak shapes. And then if you are dealing with the 3D experiment, this comma and dot will work as up plane and down plane that used to be the ZD and ZU. So that will be a very convenient 1-letter key that you can utilize for 3D experiments. And also mouse wheel mode. You can change the mouse wheel mode by type MW. Then by that way, you can use mouse wheel for zoom in and zoom out. For Mac machines, that mouse wheel acceleration is really not useful for zoom in and zoom out because by accident, if you move your mouse wheel too much, then zoom in will be too much or zoom out can be too much to see anything in your view. So by default, Mac version of NMRFAM-Sparky disables this mouse wheel mode. But if you use your own mouse with a very delicate mouse wheel, then you can use this mouse wheel mode by typing MW. On the other hand, you can just use the plus key or minus key in your keyboard to zoom in and zoom out. That zoom in and zoom out is much smaller steps than using ZI and ZO. So you can use ZI and ZO if you really need to zoom in a lot or zoom out a lot more steps. But you can still use plus or minus keys for much more divided, smaller steps than ZI and ZO. So if you press plus or minus keys, you can go a little bit more detailed than ZI and ZO. I think I did not mention about the contour level adjustment. So actually, basically, these keys are for the positive contours. But if you hold Shift key, then it will work on negative contours. So you can use shift and bracket, then you can make less gaps between the contours, or on the other hand, you can use this bracket, then you can make less crowded contours and so on. And also, yeah, like I said, arrow keys will work on your spectral view move. You really want to go upper view, then you can press this arrow or down or left or right. They will all work as a modern graphical program. So you can use those features as one-letter shortcuts. So there are enhanced street plots. So you can use 3 street plots at once. So 2-letter codes for these street plots, there are SP and large S, large P, and large S, small p. So in the past, only one street plot was available, and now you can use additional 2. So it is possible to look at, okay, I'm gonna look at carbon alpha and beta in one street plot, and carbonyl carbon in the other street plot, and protons in the other street plot, and that is possible. So you can use multiple street plots, and the 2-letter codes are actually, if you are using multiple street plots, it's confusing. So I made explicit buttons like this, so you can click the buttons instead of using 2-letter codes or going up to this menu and use the features. So if you want to make your street width a little bit broader, you can just click this button, or you want to make it narrower, you can click this button. Or zoom in and zoom out can be achieved by using these buttons, plus, plus, and minus, minus buttons, and so on. And then if you put your cursor on one of these buttons, then you will see button hint dialog. So if you put your cursor, let's say this one, then it will tell you what these buttons for. So if you have no idea what they are, then you can just get some idea from putting your cursors on those buttons. So I implemented these hints in a few plugins. Then I'm gonna try to make more hints on the other useful tools that are less documented in the future. And also scale bars, you can see the scale bars by typing VS. That's the same as the just the regular spectral view. And then once you set up that scale bar toggled on, then the next strips that you add in the strip plot automatically will have this same scale bar. So they will actually align fine on the vertical axis. So if you put your cursor on here, then you will have the same vertical position here. In the past, if you just toggle on this scale, then next one will not have this one. So these really dislocate the positions in the vertical axis, but now it is possible to just permanently turn that scale on or off. Actually, that is not in the SB Grid version, but it's going to be coming soon to the SB Grid version. And the automatic axis order. So depending on the experiment, chemical shift, range, or data point, it automatically set up the optimal axis order. So I think the solution version will work fine for C and H experiments in the SB Grid version, but so later protons and solid state NMR will be also automatic axis order feature will be in the version that installed in the SB Grid, I think. And also you can see that overlay on strips is available. So if you set up the overlay in, let's say this one is, I think, H10CACB, and overlaid with the CBCH-CONH, you can see both in the one strip like this. This one is CBCH-CONH signal, I think. And so actually you don't really need to use those two experiments set up in the one strip plots to see side by side if you are using overlay on strips. So it's going to be coming soon too. And so you set up the things to work on, and then you want to employ the automation. So the thing that you will use is automated peak picking. So well, you can use peak picking mode and then select all the peaks in the HSQC and then use restricted peak picking for 3D experiments that will introduce many noise peaks. So APES considers experimental characteristics, and then it considers across the experiments and then reduce noise peaks. So this is the thing that you can try. So you just type the number of residues. So let's say if you put 76, it's going to find the similar numbers in the NHSQC, because I mean, if you have monomeric protein that does not have though, but it's better to try its automation. It really does not harm your project. So try it first, and then it works, and you're lucky. So you select NHSQC, CBCH1H, HNCACB, and then run APES, and then it will automatically pick peaks in your spectrum, and then you refine peaks using peak list and strip plots. So this automated peak picking strategy is in the YouTube video, so you can find. So the new feature in the NMRFAM-Sparky is that you can sort the peaks by data height in the peak list. So you can change this option to data height, and then you go down below, then you will see the weakest peak from the bottom. So the weak peaks are likely the noise peaks. You validate, see it visually, and then you think that is noise, then you can delete and delete and delete until you get the robust peak list in your project. So this is another handy tool, the view list PV. So it just shows you the experiments that you have in your project, and then UCLA and data size and peaks and assigned peaks here. So this one is also telling you in the peak list dialog that 76 tells you the peak numbers in your experiments, and then this 0 means you don't have any assignment, and this 0 in parentheses means that you are not selecting any peak. So if you are selecting the 3 peaks, dragging here, then you will see 3 in here. Then if you assign a few, then you will have different number here. So that is another thing that you can see in the peak list. So once you have peak list made in your project, then you can run iPine, that is integrated Pine, which is Pine 3, basically. So it does so many things automatically. So you provide sequence and peak list. Spin system is the optional inputs, or you can have partial assignment. You can provide 3D structure for more accurate results, or if you have selective labeling, restraining amino acid types in your NHSQC, then you can provide too. So what it does is that it does backbone, sidechain assignment, and you get secondary structure information and hydrophobicity, residue-specific hydrophobicity information will be provided too. And then they all provided by the plot generation module, so you can see the plots informing you what residues are helices, what residues are buried in core, or what residues are robustly assigned, and so on. And also CS Rosetta and Ponderosa CS are all integrated in this iPine. So at the same time you run automated assignment, then you can get the 3D structures and structural restraints and noisy assignment too. So some of you may know that there is Pine. So the version that we developed in the iPine that you can see in the current Pine web page is running both iPine and Pine. We have achieved much more improved recall and precision and much less errors here, as you can see. So iPine provides much more accurate assignment while it makes less errors. That has been achieved by adapting the Ph.D. database and dynamic customization of probability density function for sidechain assignment. So with the test, we tested with the 85 proteins from the Ph.D. database with the sidechain experiments. iPine provided 4.5 more assignments with the less errors. So that is very significant improvement because this report is including all the side chains. So backbones are more or less the same. It's above 99% accuracy, but the side chain difference is huge. So iPine can assign side chains around 95% accurately for 0.5 probability cutoff, but the Pine it's about 83 or 82, so that difference is pretty big. So this is the iPine web server. You can visit and upload your pig list manually. But since I'm talking about the NMRFAM-Sparky, I'm gonna move on to this Pine-Sparky 2 GUI tool that you can use in the NMRFAM-Sparky. So the two-letter code is EP. So you just pops up this plugin, put your email here, and the sequence file automatically set up after you set up by using two-letter code SQ, or you can just browse and then select the new sequence file here. And these are the optional toggles that you can turn on or off. If you just click this use pre-assignment, then it will utilize your current assignment in your project to fix the assignment while using this iPine assignment automation. So it supports 24 experiments. You choose experiments you have and then experiment types, and click add button will add experiment in this window. In this case, I'm using NHSQC, CBCACONH, and HNCACB, and click submit button will automatically submit just to the iPine web server. Then it assigns and do the structure calculation employing CS Rosetta hosted by BMRB. So you get assignment and the structure at the same time. So you can import the results back by click this check button. So if you click that check button, and then you will see a few questions about plotting the results back in your screen. And what you will see is this kind of plotted graphs from NDP plot program included in NMRFAM-Sparky package. So you see secondary structure and the automated chemical shift reliability from Pine, and the outlier detection information. You can see these two residues flag that you want to validate next. And then the hydrophobic core predictions. So red means that that residue is buried in core. Blue means exposed to the water. So these high probability with that red are the things that really forms the structural stability. So mutation on those residues may break your protein. And also Talos N will be automatically run after the Pine assignment. So it provides random coil index that tells you which part of your protein is flexible. So under 0.7, the red, so the residue will be the reddish than other residues upper here. So that means red residues may be more dynamic than the other residues. So you can get this valuable information automatically using this Pine-Sparky 2 GUI tool. So a few hours or a few days later, depending on your protein size, you get the CS Rosetta results. So iPine runs the CS Rosetta hosted by BMLB. And then in many cases, you don't get the convergent structure. So you may need to proceed to the NOE-based structure determination. But it's also useful to just see the overall fold that may or may not be really matched with your real structure, but it's better than nothing though. So so it gives you the 3D structure from the CS Rosetta. Well, like I mentioned in iPine, it also calculates the 3D structure based on the NOESY. So there are two additional NOESY-based experiments, N15 filter NOESY, C13 filter NOESY, that you can use as inputs in the iPine. So you select N15 NOESY, C13 NOESY, and then click the submit button, then you can get the structure from the Ponderosa CS. It runs Ordena algorithm for automated NOE assignment. This is the example that I ran for mouse thiamine 3-phosphatase. It's 24 kilodalton of protein. 97% of all the assignments, including sidechain, has been achieved. And then I got this structure all automatically. I didn't do anything else than picking and running this Pine-Sparky 2. So they can be used, and also intervening at any moment is also possible. So if you want to do the, okay, I'm going to do the backbone first, and then sidechain, and then structure calculation step by step, then it's possible because it accepts this pre-assignment option. Also, you can run Ponderosa client separate from this Pine-Sparky 2 plugin, so you can finish your assignment first and then move on to the Ponderosa client program that also comes with the NMRFAM-Sparky, that you can customize your run more refined way using RDC or SAS data or your own angle constraint or some other customized distance restraints altogether. So it's very flexible and also a fully automated platform that you can easily use. So you may want to look at these new automation tools. So this is my last slide. So NMRFAM-Sparky, you can teach yourself by using the documentation you can find. In the program, you just type HN, then you can see these two-letter commands. Many of them were already covered in this talk, but sometimes you need to recall these two-letter codes or one-letter codes, then you can find using this shortcut manual. And then video tutorials, just typing large T, you will see this YouTube video playlist, so you can teach just watching these videos by yourself. And also there is a Sparky user forum. So two-letter code in the Sparky is large S, large F. And we hold annual NMRFAM workshop for learning assignment, how to use the Sparky program, Ponderosa CS for structure determination, and also particularly in this year, the one-day head workshop by Professor Bonvin will be held right after the NMRFAM workshop, so you may want to Google our workshop. So this is the end of my talk. So I'm gonna take any questions really regarding using NMRFAM-Sparky or this talk. Thank you.
Great. Thank you very much, Woonghee. That's very impressive. So if there are any questions, you can send them here by chat, and I can pass them along. It's great to see so many features that can improve and enhance the progress of assignment. And I think anyone who's gone through and done a manual assignment can appreciate that having a quick key for every possible display and every option can really speed up your workflow. You can almost get into a place where your hands know the quick keys before your brain does, and you can sort of navigate through your spectra really seamlessly. I had a couple of questions. One, so for the Pine, iPine, the automation tools, what would you say would be the sort of, you know, everybody's data is always, you know, a little, we all want ideal data, but we rarely get it, right? So let's say you've got a little conformational heterogeneity, or let's say you have other issues. What would you say would be sort of the things that you think trip up the automation, and what gets handled pretty well?
Well, I mean, the iPine only considers pig list, not the spectrum itself. So, well, providing the punctual pig list is pretty important. So, I mean, well, last year I published a paper about the Pine-Sparky 2, and I used the AESCP2 protein that has a little bit of conformation. So the other conformation, then I just neglect and then selected the major ones to run the Pine, and then next to that, then you can adjust. So the peaking and then make the peaks aligned is very important. So I always recommend, let's say if you pick the peaks in CBCA-CONH, in many cases, you don't see the peaks HNCA-CB if your protein is dynamic. Then if the peaks are pretty robust, then I would just copy and over onto this HNCA-CB. That can be easily done by ornament copy and paste, OC and OP. So even though you don't see the peaks in the other experiments, and then you see that signal in the other experiment, then you should have them in the experiments that you don't see, because by that way, iPine can get the more robust assignment and accurate assignment. And also, by using that Pine-Sparky 2 plugin, you can turn on use pre-assignment toggle on, so you can achieve gradual improvement in your assignment by employing iterative auto-assign. So you just run iPine initially and then get some assignment back, and then refine a few and then get some more assignment by your hand, and then you can just rerun iPine again. It's not a big deal. You just check the pre-assignment and click the button. Then you get more assignment and more assignment and more assignment. So really the clever use of the tool will make your life much more easier.
Yeah, so it's the standard iterative approach to assignment. Yeah. So one other question that I had is the integration with Talos N and CS Rosetta it's hard to underscore how much work that could save someone from a just purely configurational perspective of getting all those tools to run. Those are open to all academic groups, and about how long does it take for one of those jobs to run? You said 3 hours to a couple of days. Are there limits on protein size and job length?
Well, Talos N does not really require a lot of time.
Yeah. But CS Rosetta does, I think,
CS
right?
Rosetta, BMLD utilize HT Condor system and Open Science Grid that has been developed in University of Wisconsin. And for, let's say, for the ubiquitin, it would take like 3 or 4 hours, and maximum 7 or 8 hours, I think. But if your protein is big, like well, let's say if you have 50 kilodalton, it's not really big for other biophysical method, but for NMR, it's really big protein. But 50 kilodalton protein, let's say it'll take a week, I think. So it really depends on your protein size, and I think also if you have fragment in the database really matches with your protein, it will reduce the time. But I did not really do the systematic evaluation of stress Rosetta by myself, so I don't know.
Yeah. All right, great. Well, with that, Woonghee, thank you very much for the great software and the great webinar. And everyone, I encourage you to check out the workshop for this summer, especially if you get a 2-for-1 haddock NMRFAM-Sparky workshop. That seems like a special deal that one should take advantage of. And with that, we'll close it up. Thank you again.
Thank you, my pleasure.